Hi all, welcome back to the series of lecture on the topic sequence and series. This is our sixth lecture in this topic. Let us begin by recalling that the two words sequence and series are used interchangeably in day-to-day life. Both these words are used to indicate succession of events. That's why I told series of lectures. However, it should be borne in mind that these two words sequence and series have distinct meaning in mathematics. Roughly, sequence is used to indicate list or succession of numbers, and series is used to designate sum of terms of a sequence. Having said this, as promised in the last lecture, we shall establish a formula for sum of n terms of a GP. Recall that a GP, geometric progression, is a sequence in which each term after the first term is obtained from the previous term by multiplying with a fixed non-zero number, and that fixed non-zero number is termed common ratio of the geometric progression. Next, we shall establish a formula for sum of n terms of a geometric progression. Let us consider a GP with first term A and common ratio R. Note that a GP with first term A and common ratio R can be explained or represented by the list A, AR, AR square, etc., nth term A R power n minus 1, etc. Our goal is to find a formula for A plus AR plus AR square plus etc. up to the nth term, namely A into R power n minus 1. Let us denote this sum by Sn. What we intend to do is to find a formula for Sn. Let us first settle the trivial case, namely let R equal to 1. Note that in this case the geometric progression reduces to the constant sequence A, so on. Consequently, Sn is A plus so on plus A n times. That is, Sn is equal to n times A. This settles the trivial case. Now let us consider the remaining case. Let r not equal to 1. What we want is a formula for Sn equal to a plus ar plus etc. up to a r power n minus 1. We shall use a simple trick as follows. Let us find r times Sn, which coincides with ar plus ar square plus etc. The last term when multiplied with r becomes a r power n. Let me write the previous term for you. It will be a r power n minus 1. Do you see it? Now let us subtract the second equation from the first. That yields Sn minus r Sn equal to, see that the terms ar, ar square etc. ar power n minus 1 cancels in this subtraction process. We end with a minus a r power n. The left hand side boils down to 1 minus r times Sn, and the right hand side can be simplified to a times 1 minus r power n. From this we can easily isolate Sn. Recall that by assumption r is not 1, so division with 1 minus r is possible. Doing so, we get Sn is equal to a times 1 minus r power n by 1 minus r. To sum up, sum of first n terms of a geometric progression with first term a and common ratio r is n times a if r is equal to 1, and a into 1 minus r power n by 1 minus r if r is not equal to 1. Observe that when r is not equal to 1, we can write the formula also as a into r power n minus 1 by r minus 1, just by multiplying numerator and denominator with minus 1. So, this is a nice formula for sum of n terms of a GP. I hope this is a good time to remind you about an infinite sum or a series. To be more precise, what are all the troubles in extending the concept of finite sum to an infinite sum? Note that when we have a finite sum, that is sum of finitely many real numbers, we can add first two of them and to this sum we can go on adding one term each time. The process will terminate and we will be getting a finite value. Further, when we have a finite sum, the order in which the terms are added does not really matter. Whereas, if we have an infinite sum, note that we cannot go on adding one term at a time to see what comes out. For the obvious reason that the process of adding one term at a time will not terminate. Secondly, unlike the case of a finite sum, we observe that in an infinite sum, the order in which the terms are considered while performing the addition matters. In other words, to deal with sum of infinitely many real numbers, first the real numbers should be ordered in some definite manner, and ordering of real numbers give rise to a sequence. Thus, to define an infinite sum, we should start with a sequence of real numbers rather than just a set of real numbers. Given a sequence of real numbers, an, n is equal to 1 to infinity, the expression a1 plus a2 plus etc., which can be written for brevity using summation notation as sum n equal to 1 to infinity an, is called a series. Now, how do we assign a meaning for this expression? Recall that to assign a definite meaning for this expression, we first find the sequence of partial sums. Sn is equal to a1 plus a2 plus etc. plus an. Thus, we have a new sequence Sn, n is equal to 1 to infinity, which originates from the given sequence an. Now, we observe what happens to this sequence of partial sum as n becomes large. To be precise, we find limit n tending to infinity Sn, whether the terms of the sequence become close to a fixed real number as n becomes larger and larger. That is what we investigate. If this limit exists and if it is yes, then this yes is regarded as sum of that series, or precisely the value of the series. We write S is equal to summation n is equal to 1 to infinity a n, and we say series a n is summable, or more technically convergent. Thus, to see whether an infinite sum has a meaning, in other words, whether it is summable, in other words, whether a series is convergent, we should first find sequence of partial sums. Then we investigate what happens to this sequence of partial sum as n becomes larger and larger. Keeping this in mind, let us try to tackle sum of an infinite series, namely a geometric series. By a geometric series, we mean series originating from geometric progression. Remember, a geometric progression is a sequence of the form A, AR, AR square, and so on. Now we deal with its sum. Series of the form A plus AR plus etc. plus AR power n minus 1 plus etc. The infinite series, which can be written as summation AR power n minus 1 n is equal to 1 to infinity, is called geometric series. Now the question is whether a geometric series is summable, whether it is convergent. Note that summability of a series amounts to finding whether the sequence of partial sums is convergent or not. As far as this geometric series is considered, the sequence of partial sum, namely the sum of first n terms, is already found. We have a formula for it. Note that Sn, the sequence of partial sum, is Na if r equal to 1 and a into r power n minus 1 by r minus 1 if r is not equal to 1. Hence, to answer whether a geometric series is summable, that is, whether finally it represents a finite number or not, it is enough to investigate what happens to this sequence of partial sum Sn when n becomes larger and larger. Let us do that. Let r is equal to 1. The common ratio is 1. Note that in that case Sn is equal to Na. Recall, a is a fixed real number. Therefore, As n becomes larger and larger, Sn, namely Na, becomes large in magnitude. It should be clear that as n tending to infinity, Na tends to infinity or becomes very large or becomes very small depending upon sign of A. Let me write limit n tending to infinity Sn is equal to plus or minus infinity depending on sign of A. This is the case r equal to 1. So, in this case we observe that the sequence of partial sum is not becoming close to a fixed real number, finite real number. In technical language, limit Sn does not exist. Therefore, the geometric series is not convergent or not summable in this case. Let us take the special case r equal to minus 1 next. In this case, the geometric progression becomes A, next is AR which is minus A, next is AR square which is A, and so on. Consequently, S1 will be A sequence of partial sum, first one. Second sequence of partial sum will be first term plus second term, A plus minus A, which is 0. The third sequence of partial sum will be A plus minus A plus A, which is A, and so on. You should be able to observe that the sequence of partial sum Sn alternate between A and 0. What I mean is, it takes these two values alternatively. Intuitively, from this, it should be clear that as n becomes larger and larger, Sn does not become close to any number. It will go on oscillating between A and 0. It will be either A or 0. It will not remain fixed, close to a fixed number. So, in this case, limit n tending to infinity Sn does not exist. As the sequence of partial sum does not have a limit, we conclude that in this case the geometric series summation A r power n minus 1 is not summable. Roughly, this series does not represent a finite number in case r is equal to minus 1. Now, let us take the other case, r is neither 1 nor minus 1. Observe that in this case, sequence of partial sum Sn takes the formula A into 1 minus r power n by 1 minus r. what we have to observe is what happens to this Sn when n becomes larger and larger. Note that Sn can be written as a by 1 minus r minus a r power n by 1 minus r. Obviously, the first term is independent of n. So, to investigate what happens to Sn as n becomes large enough, it is enough to investigate what happens to the second term as n becomes larger. To be more precise, it is enough to see what happens to r power n as n becomes larger and larger. To do so, let us split the values of r which we are interested, namely r not equal to 1 comma minus 1, into two categories. One, mod r strictly less than 1, that is, we are interested in those values of r lying between minus 1 and 1, both excluded. When mod r is less than 1, of course, r can take both positive and negative value, but then since it is less than 1 in magnitude, it will be of the form 1 by some m. R will be of the form 1 by m, where m is fixed. Do you agree? So, as n becomes larger and larger, r power n, that is 1 by m power n, becomes smaller and smaller. Do you see it? Because in 1 by m power n, the denominator becomes large enough as n becomes larger. So, my conclusion is that in this case, limit n tending to infinity r power n is 0. Let me repeat. We are interested in r values which is fixed but lying between minus 1 and 1. In that case, r can be thought of as some number of the form 1 by m. M may be positive or negative, does not matter. So, r power n will be something of the form 1 by m power n. M is fixed. Now, when n becomes larger, the denominator becomes very large, so that 1 by m power n become close to 0. That is how intuitively you can argue limit n tending to infinity r power n equal to 0. Due to this, going back to Sn, we can observe that as n becomes arbitrarily large, the second term become close to 0 as we have limit r power n as n tending to infinity is 0. Therefore, the second term contributes nothing as n becomes large, and we deduce that limit n tending to infinity Sn boils down to a by 1 minus r. If you recall the definition of an infinite series, or more specifically convergence of an infinite series, limit of partial sum is what we call as sum of the series. Therefore, in this case, we conclude that summation a r power n minus 1, n is equal to 1 to infinity, sum of all terms of a GP is a by 1 minus r. So far we discuss only the case r equal to -1, r equal to 1 and the case r lies between -1 and 1. Now let us take r to be some fixed number outside these values, that is, let mod r greater than 1. R can be positive or negative, but in magnitude it is greater than 1. Now see that limit n tending to infinity mod r power n. Since r is outside -1, 1, mod r is greater than 1. So as n tending to infinity, you have that mod r power n becomes large and large, something like 2 power n. You can see that 2, 4, then 8, then 16 and so on. As n increases, the power increases indefinitely. Therefore, this is infinity. Keeping this in mind and going back to the expression of Sn, one can see that as n becomes large, this term, namely the second term a r power n by 1 minus r, does not become close to a fixed real number. In other words, it is not convergent. Therefore, limit Sn also does not exist. Therefore, limit n tending to infinity Sn does not exist. To put in language of series, this is equivalent to say that the corresponding series is not summable. That is, summation a r power n minus 1 n is equal to 1 to infinity is not convergent. In the case mod r greater than 1. Let us sum up. For a geometric progression, we have an expression for sum of first n terms, and the expression is Sn is equal to a into 1 minus r power n by 1 minus r for r not equal to 1, and for r equal to 1 it reduces to a trivial case, namely Sn is equal to n times a. Now considering an infinite geometric series, summation a r power n minus 1 n ranging from 1 to infinity, we see that when r equal to 1, the series is not convergent. When r equal to minus 1, the series is not convergent. The geometric series do represent a finite value when r lies between minus 1 and 1, and that finite value is a by 1 minus r. And for mod r greater than 1, the geometric series does not represent a finite value, or more technically, the geometric series is not convergent. Let me record this observation here. A geometric series of the form summation n equal to 1 to infinity a r power n minus 1 is convergent if mod r is less than 1. Further, for mod r less than 1, mod r less than 1, the sum of all terms is a by 1 minus r. For other values of r, that is mod r greater than or equal to 1, summation n equal to 1 to infinity a r power n minus 1 is not convergent. I would strongly recommend you to remember this result. An infinite geometric series is convergent if the common ratio lies between minus 1 and 1, excluding these two cases, and in that case the geometric series sum to a by 1 minus r. And for mod r greater than or equal to 1, the geometric series is not summable. Let me make a passive remark here. Note that in the case of an infinite geometric series, we observed when it converges and when it does not. Moreover, in case it is converged, what is sum of a geometric series? These things we observed. Unlike geometric series, in many other infinite series, the question of whether the series is summable or convergent, even if it is convergent, what is its sum? These two questions are tackled in two steps in case of many infinite series. First, we shall investigate whether the series is convergent or not. In case it's found to be convergent, most of the cases we have to be satisfied with some estimate for its sum rather than getting an expression for sum. In other words, a formula for sum of infinite series like that in the case of geometric series is rare. Let us proceed. Recall that given two real numbers a and b, we asked a question: can we insert a number capital A between a and b so that these three numbers forms terms of an arithmetic progression? In fact, we had a formula for A. A plus B by 2, and we called this number as arithmetic mean of A and B. AM for short. We shall ask a similar question, but now instead of AP, a GP. That is, the question reads as, given two real numbers A and B, does there exist a number, let us call G, such that A, G and B forms a GP? Hope you understand the question. You are supplied with two numbers. For the time being, let us not impose any condition on A and B except that they are reals. Question is, can we always find a number G such that A, G and B forms terms of a geometric progression? Let us settle this question. Note that if A, G and B are terms of a GP, consecutive terms of a GP, the ratio of second term by first term should coincide with the ratio of third term by second term. That is, G by A coincide with B by G. If A, G, B are in geometric progression, that is equivalent to say G square is equal to AB. So, we are asking the question, does there exist a number G such that G square is equal to AB? Note that square of a real number is always non-negative. Therefore, for existence of a real G satisfying G square is equal to AB, A and B should have same sign. So, let us slightly modify the question and ask ourselves, given two positive numbers A and B, does there exist a G such that A, G, B forms a GP? Answer is yes. Take G to be root of AB. In this case, A, G, B forms a geometric progression, and this G is referred to as geometric mean of given positive numbers. Let me record it as a definition. Given two positive numbers, capital A, let me write small a and small p, the geometric mean GM for short of A and B is defined as GM of A and B is equal to root of AB. This is similar to arithmetic mean. In case of arithmetic mean, we have addition and division. We add and divide by 2. Here you have multiplication and taking exponents, taking powers. To sum up, given two positive numbers A and B, you can always get a number capital G, namely the geometric mean of these two numbers, so that A capital G B forms a geometric progression. Now let us generalize this a bit and ask the following question. Given two positive numbers A and B, can we insert as many numbers as we need but finite such that A, G1, G2, etc. Gn, B forms a geometric progression. Given two positive real numbers A and B, we would like to insert n real numbers which we designate G1, G2, etc. Gn, so that A, G1, G2, etc. Gn, B forms a GP. Towards the answer, let us observe the following. If we need A, G1, G2, etc. Gn, B to form a geometric progression, more precisely consecutive terms of a geometric progression, B should be n plus 2th term of that geometric progression. B is n plus 2th term. We have a formula for nth term of a GP with first term A and common ratio R. Letting common ratio of the desired GP to be R, the n plus 2th term is given by the formula A R power n plus 2 minus 1. That we need to be B. So, R power n plus 1 is equal to B by A, which amounts to R equal to B by A the whole power 1 by n plus 1. Now we have the first term A and common ratio this thing, B by A power 1 by n plus 1. Once we have first term and common ratio, we can completely specify what is the geometric progression is. Therefore, G1 being the second term of the geometric progression will be A times the common ratio, which is A times B by A the whole power 1 by n plus 1. Similarly, G2 will be being third term of the geometric progression, it will be A times R square, which is A times B by A the whole power 1 by n plus 1 square, and so on. Thus, we conclude that given two positive numbers, it is always possible to insert finitely many real numbers between them so that the list forms a GP. We shall continue with GP and AP in the next lecture. Thank you.